before lunch. So first up, we have Mathilde Mingozzi, who is at Space Telescope.
Can you hear me? Can you hear me well? No? Okay. Maybe can you hear me like this? I will do that. Okay. Hi, everybody. Done. Hi, everybody. First of all, thank you very much for the organizers to give me the possibility to present my science today. I'm Mathilde Mingozzi. I'm an ESA-hour astronomer at Space Telescope Science Institute, which means that half of my time I support HST as a part of the STIS team. The other half of my time I do science, and today I want to talk about ISM properties of high-redshift analogs to interpret the epoch of reionization using HST, which is my past and current work, and using JWST, which is part of my future work, Visual Perspectives. So I will start again, we will see this for the second time today, or maybe more, with the cosmic timeline showing the main epochs of the history of our universe, and with some open questions that we still have concerning the high-redshift universe. In particular, we still don't know what properties characterize the first galaxies and how did they reorganize the universe, among the other things. And now, with JWST, it's incredible on how many new galaxies we are discovering. We saw this in the talks before. We have we have hundreds now of galaxies at redshift higher than 8. And here I just wanted to show two examples of two high redshift galaxies, one at redshift 12.5, one at redshift 10.6, where you can clearly see also emission lines, and we can use these emission lines to understand better the properties of these systems. However, the majority of these emission lines are in the rest frame UV, that is redshifted at redshift higher than 6 in the infrared observed wavelength that JWST is targeting. And in order to interpret then the properties of these systems using their emission lines, we need to understand how to use the UV as diagnostics. And the best way to do this is to use the local universe as a comparison, because in the local universe we can observe the rest frame UV with Hubble Space Telescope. We can get very high resolution spectra and high signal to noise spectra, and compare them also with multi-wavelength, with the other bands like optical, infrared, and so on. This is why I will present you the work that we have done studying analogs in the nearby universe in order to better understand the high-redshift universe. And I will do this by presenting the CLASSI survey. CLASSI stands for Cost Legacy Archive Spectroscopic Survey, and it represents today the largest survey of star-forming galaxies with 45 objects, with full rest frame FAR-UV spectral coverage and high signal to noise. This is one of the spectra of the CLASSI survey, where you can see that we cover from the Lyman alpha up to the carbon 3 at 1909 angstrom, more or less. We can see plenty of absorption and emission lines, spectral features related to massive stars, related to ISM outflows, related to very high ionization gas. These galaxies were selected to span a broad range of properties, including properties that we see in the high-redshift universe. Here I will show you just one example. There are more information in the presentation paper from Daniel Berry, 2022. But you can see, for example, the star formation rate as a function of the stellar mass for the CLASSI galaxies, shown in as purple dots here. And these galaxies have generally higher star formation rate than the local universe, that is represented by the turquoise and blue line, so they are more comparable to the high-redshift universe. They also span a broad range of gas phase metallicities, going even to very low gas phase metallicity, like a few percent solar, which is comparable to what we observe at high-redshift. My role within the CLASSI collaboration was to analyze the optical and the UV spectra, study the emission lines, compare the optical and the UV, and understand if we can create a UV-based toolkit to understand the gas properties of the interstellar medium. I will start by showing some results concerning density diagnostics. So using the optical, you have plenty of lines that you can use as density diagnostics. For example, the sulfur 2 lines or the oxygen 2 line ratios. Using these diagnostics, we can get densities that are around 100 centimeters to the minus 3 with peaks around 1,000 for our galaxies. But using for the same galaxies, using UV density tracers, which are, for example, the carbon-3 doublet, the silicon-3 doublet, or the nitrogen-4 doublet, we can get densities that are up to 2 decs higher. The reason why this is happening is because these tracers are tracing different ionization regions. The sulfur 2, of course, is tracing the low ionization region, carbon-3 and silicon-3 more the intermediate, the nitrogen-4 the ionization region. So the take-home message from this is that when we compare properties of the high redshift universe and the local universe, we need to take into account that we are looking at the same ionization zone. Moving to other properties, for example, the gas phase metallicity or the ionization parameter. I tested among the UV lines, UV line ratios equivalent with which could be the best indicators. There is some scatter because UV lines are sensitive to the gas phase metallicity, but also to other properties, including the ionization parameter. They are very sensitive. They are very temperature sensitive and also high ionization lines. But the best relation with some scatter that I could find is the relation between the gas phase metallicity and the equivalent width of the carbon-3, with the equivalent width of the carbon-3 increasing, going at lower metallicities. There is a turnover of the relation below 7.5, so this should be used with caution, but could be a possible good diagnostics for a gas phase metallicity at higher redshift. For the ionization parameter, instead, this is one of the relations proposed in my recent paper, and that is with the equivalent width of the carbon-4, and if you are interested, there are more information over there for other diagnostics. Another important property to study is the main source of ionization, of course, in galaxies. Classic galaxies were selected to be star-forming, and in my more recent paper, I tested different optical diagnostics to confirm that they were star-forming, and they were. And these are two diagnostic diagrams I used. There are more in the paper. This is the N2 BPT diagram, the very famous diagram that compares the oxygen 3H beta versus N2H alpha, and the helium 2H beta versus N2H alpha. The take-home message from this is that the classic galaxies are classified as star-forming, despite also taking into account their metallicity, which leads, for example, the Q solid line here to move because of the gas phase metallicity. But still, the classic galaxies would stay in the star formation locus, even taking that into account, and especially their helium 2H beta is clearly in the star formation locus according to the Shiraz and Brinchman diagnostic diagram. So what does it look like in the UV? In the UV, I tested different diagnostic diagrams. This is currently the best one that I could find that compares the carbon-3 helium-2 versus the oxygen-3 helium-2. In general, the oxygen-3 helium-2 seems to be a good light to take into account because it allows to separate better between AGN and shock models. So the oxygen-3 helium-2 or the oxygen-3 carbon-3 are good line ratios to separate between the two different models. And in this diagram, the classic galaxies are clearly located away with respect to the two models in this region over there. Even the most metal-poor systems, that are these two objects over here, that are close to the edge of what I defined as star formation locus, but still they are not superimposed to AGN and shock models. While if you use different diagnostic diagrams, you have to take into account that the most metal-poor system could fall on AGN and shock-dominated models, so there could be a misclassification over there. This is just to give you an overview about all the other works that have been done on the classic survey. So it's not only the UV diagnostics, but there are works that studied ionized outflows, Lyman alpha profile, low ionization UV emission lines, abundances of different elements, and many more coming. So and if you want to find more information about this, you can check the web page. and the mass portal. And it's good to see that, that some of the UV diagnostics and some of the knowledge got from Classi has started to be applied in high redshift works. For example, there is this work from Lerena 2023 on bandes at redshift 2 that showed that the equivalent width relation with the metallicity could have a different offset, which needs to be more investigated, better investigated. While this work from Castellano 2024 showed some of the most high redshift systems, which are still for which is still unclear if they are AGN or star-forming galaxies, which apparently lie very close to the edges of the separators I showed you before, which probably means that these are very metal poor systems, and we need to further investigate the real ionization source. But what is the next step from all these Classi study of UV diagnostics? I think that the next step is to expand the UV toolkit, taking into account spatially resolved data. And I say this because I think about all the things that we learned using integral field spectroscopy in the optical, which has really revolutionized our way to diagnose physical and chemical properties in galaxies. I think, for example, at all the FANGS results, at the MANGA survey, which allowed, for example, to understand that if you have low ionization emission lines, depending on the extension of the region, you can have a different classification, or all the chemodynamical studies that have revealed chemical inhomogeneities, which can be interpreted as signs of accretion and or enrichment. So the question is, can we do similar studies in the restrained UV with HST or with the future UV missions, which are currently UVEX and the Habitable World Observatory? So it is very crucial, it is very challenging, to use HST, but it's possible. This is my actually work in progress. You need a lot of time to do this. So basically putting together 2 main programs and also some archival data, and so collecting more than 50 hours and 12 filters per galaxy, you can do a spatially resolved study of Lyman alpha, carbon 4, and carbon 3 for 3 objects. So you need a lot of time, but you can do it. And for this, we are using filters from ACS, STIS, and WFC3. The reason why we need spatially resolved data that go beyond the COS aperture that is shown here, that is of 2.5 arcsec. It is pretty clear in this oxygen-3 image of the galaxy J1044 that is shown in green over here. It has this damped Lyman alpha emission, absorption with a tiny emission, and then strong carbon 4 and carbon 3. If you look at the oxygen-3 map, clearly the majority of the emission comes from the COS aperture, comes from the region covered by the COS aperture, from where this spectrum comes from. But there is definitely something more coming, like from the surroundings, and also within the COS aperture would be interesting to understand how the UV emission line changes, because these 3 objects that I'm showing you here have similar properties. They are all metal poor. They have similar properties, but clearly they have very different Lyman alpha profiles and also very strong carbon 4 and carbon 3 emission lines, but different line ratios. So how do we do this? First of all, I want to say that for this work, I'm also collaborating with Aidan Pigeon, with the science support analyst at Space Telescope, because there were a lot of technical difficulties in this project, including filter alignments, drising all the filters with 3 different instruments with the same spatial scales, PSF matching, and so on. But basically, the main difficulty is that in the UV, there are no UV narrow bands on HST. And so what you can do to study the Lyman alpha and the carbon 4 is that you can use SBC, ACS SBC band passes these are filters that have this peculiar shape. And basically, using multiple of them, you can have like synthesized narrow bands. Selecting only the Lyman alpha and the carbon 4 in these 2 filters over here. And in order to then isolate the contribution of the emission line, you need to do a very detailed LCD fitting, pixel by pixel or bin by bin, and to really isolate the contribution of the emission of these two emission lines. Concerning the carbon 3 instead, the situation is a bit different. You need to use STIS instead because there are no filters on ACS. For STIS, there is one filter that is covering the carbon 3. It has a very low throughput, so it is this thing over here, very tiny. But it is covering the carbon 3 emission. And also here you need to do a pixel by pixel estimation of the flux in each point in order to try to get this emission line in this very broad filter. I will show you very preliminary results that I am getting that are very promising though. This is the J1044, that is the galaxy that I was showing you before, the one that had the dumped emission of Lyman alpha and a tiny, dumped absorption of Lyman alpha and a tiny emission. And you can see that in the cos aperture shown over here, there is absorption of the Lyman alpha in the center, and there is a hint of emission coming from the surrounding regions. The carbon 4 is still unclear. I'm still working on the LCD fitting, but it appears that he is in emission in the central region where there is the majority of the UV light coming from. And the carbon 3 has an emission that is much more compact, which is expected, and is coming probably from only these two tiny peaks that are within the cos aperture. This is work in progress. I am currently working on optimizing the LCD fitting and interpret the results. Also for the other two objects of our program, and the main thing we want to do is to compare the spatial distribution, the morphologies, to understand differences and similarities, creating the first carbon 4, carbon 3 line ratio maps in the local universe, in order to map the ionization sources and also understand if we can find further Lyman continuum escape tracers with respect to the Lyman. Before concluding, I just want to mention something about the future of UV spectroscopy, what we are expecting, like beyond HST. One of the nearby future is represented by UVEX, that is the NASA's next astrophysics medium class explorer mission. UVEX will be 50 times more sensitive than GALEX, and it will have a far UV and near UV imaging, all sky survey, and spectroscopic capabilities as well, which is really cool. UVEX has many, has three main goals, three main science cases. I am part of the low mass, low metallicity galaxy frontier. And so now I will show you a couple of things related to these, but there is much more, so if you are interested, please go and check the website. For example, for the low mass, low metallicity system, UVEX is expected to find many objects in this discovery space that is currently not very well sampled by, especially because in the UV. HST doesn't have enough sensitivity to study this very metal poor system, very metal poor with low masses and very young. You can see here, for example, what is expected from the sensitivity of the spectrograph of UVEX with respect to what is currently available on COS. So you can see how better we should be able to identify emission lines in the UV, and thus in this way we will be able to reveal for the first time UV spectra from the Lyman alpha to the carbon 3 of nearby low mass, low metallicity galaxies up to redshift 0.38, which is something that we currently cannot do. UVEX is expected to launch around 2030, but the thing that is missing on UVEX is that we will not have a UV IFU or a UV MOS in order to do spatially resolved spectroscopy. We can still do something with the slit probably, but not at super high spectral resolution. So for a UV IFU, hopefully, or a UV MOS, we need to wait for the next NASA flagship astrophysics mission, that is Habitable World Observatory, which is expected to come around 2035. 2025. And before concluding, I just want to give a brief overview of the future work that we want to do on these local iRedshift analogs. We are planning to use MIRI data that we collected for 6 of the class C galaxies, MIRI MRS data. In this way, we will be able to map also the infrared spectra of these systems, basically mapping the entire galaxy, more or less, because these objects are quite compact. So we will do something that is spatially resolved, not in the UV, but in the infrared. The really cool thing about this is that the mid-infrared is full of emission lines with different ionization potential. So using MIRI, we can really explore the ionization structure of these systems. And the mid-infrared is also full of, there are also H2 rotational lines, which means that we can also explore the molecular gas phase of these objects, which is another thing that is very important in order to characterize these iRedshift analogs. And putting together MIRI with the ALMA and IRAM programs, with ALMA and IRAM data available for these objects, we will also be able to compare the warm molecular gas with the cold molecular gas. And learn more about the reservoir of gas that they have to form stars. And really, to conclude, I will leave you here with my conclusions and future perspective. I just want to highlight that class C is very useful to get insights on UV spectra of iRedshift analogs in the local universe, and that we developed this UV toolkit, but there are also many more information. So if you want to see more about the SAM outflows, about Lyman alpha studies, please go and check the papers that have been published from the collaboration. And the work in progress is to try to have UV spatially resolved diagnostics for the first time in the nearby universe, and also to explore the mid-infrared and sub-millimeter counterpart with MIRI and ALMA. So thank you very much for your attention, and I'm happy to take questions.
All right, thank you. All right, we have time for a few questions. Anyone? Okay, great. Mark?
Right, so for the part looking at the molecular gas, what is your strategy for coping with XCO and its unknown but probably very big value when you go to low metallicities? Have you thought at all about how to deal with that?
Yes, absolutely. So in fact, that is the reason actually why, because this is it was a slide that I made. There is this very nice cartoon from Madden 2020 that clearly shows that the CO distribution in metal poor systems could be really different because with the, of course, higher radiation field, you would expect CO to be much more dissociated, and so probably it's not the best way to diagnose the molecular gas in these very metal poor systems. The thing is that we actually don't have too many studies targeting CO in this metal pool system because it takes a lot of ALMA time, which is why we tried many times to get ALMA time, and it was difficult to get it because of course it can be risky. But we got now approved two proposals, one in cycle 10 and one in cycle 11. The one in cycle 10 was not completed, so hopefully we will get some detection of CO10 and CO21 for a sub-selection of these systems in order to study how the CO emission changes with properties of our galaxies, and we hope to learn more about also the alpha CO. And putting this together with MIRI allows to study the H2 lines. The H2, they trace the warm molecular gas, not the cold phase, but doing some assumption, our aim would be to have an estimate of the cold molecular phase and then compare it with what we get from the CO. So from there, we would like to learn something more about what you were suggesting. So I don't have an answer now, but hopefully I will in a couple of years.
All right. I think we're gonna, in the interest of time, we will move on, but thank you for advertising all this upcoming work. So let's thank our speaker again.
Thank you.